it's lovely to be back. I was last here in 2008 when I was working still in physics. The talk I'm going to give, it's really nice to be here at PI for the next couple of days because it's rare that I get a chance these days to hang out with so many physicists simultaneously. So I hope you will take the opportunity to track me down and ask me questions or tell me things that you think I should know, even if they seem very obvious to you, because over time, there's some exponential decay about how much physics you know, sadly. One of the major innovations of physics after 1950 was the discovery of renormalization. It was probably the greatest thing that physicists did after the war. And renormalization is a general set of tools that help us understand how theories simplify, right? They tell us how to throw out, and I'll just say this in a very abstract way. I'm sure you know exactly how they're used, for example, in QED, how to throw out information that you may not know, that you may not be able to know because your collider is not big enough, you don't know the fundamental theory, or that you may not care about. It depends, I suppose, if you're interested in sort of waves on a table or the underlying structure of the podium itself. But throwing out information is not enough. You have to throw it out correctly. And so this talk is about how to throw out information, how to simplify theories in cases where the physical intuitions that we have no longer operate. Systems such as cognitive systems, systems such as social systems and biological systems. So to give one sense about how long, in fact, we've been thinking about this problem in the social case probably much longer than we had in the physical case. Isaac Newton presumably never asked what was more fundamental than the 1 over r² law. But if I can blow up this image, this is from a 17th century book called The Leviathan by Hobbes, Thomas Hobbes, who you may know as the inspiration for the character Hobbes in Calvin and Hobbes. There's actually no relationship between this nice tiger and Hobbes himself, who understood society as this battle of all against all, this awful state of nature that we have to solve through the invention of politics. But what I love about this image is if you look closely, this is the sort of body politic, right, this king here. But if you zoom into this image, and this was written in the 1680s, you'll see that this man is actually made up of lots of little people. And so even very early on, we understood that if we wanted to talk about politics, we had to understand how individuals combine together to make politics. In order that politics itself makes sense, in order that Hobbes can talk about a theory of politics, we must be able to build theories of politics that are somehow independent of all these microphysical details, all the details of what individuals believe and what individuals think, right? If it was impossible to have a predictive theory about what society would do without knowing every single thing everybody is thinking, then politics would really have no meaning. All we would be able to do is simulate every single person in the nation. But instead, we do believe, or at least Hobbes believed, and many of us believe, that in fact there is some sense to the idea that you can coarse grain or throw out all these minds here. You can throw out most of what goes on in these brains and most of the interactions between these individuals to develop a theory of the society as a whole, a theory that would hopefully be much, much simpler than the 300 million people, 400 million people in North America. Okay. So this talk is a story about how to do that. And at the end, I will actually tell you a story that we've told, that we have in review, so we're very excited, a story about politics and the coarse graining of politics, the coarse graining of the individuals to produce politics. It actually is not a human system, it's an avian system, it's birds. So we'll talk about the political lives of birds at the end. So that's the prize if you stick with me. As I remember my physics, right? So what we want to do is we want to average things. We want to throw away small-scale information to build a theory like this, to build quantum electrodynamics, right? This is a gauge-coupled spinner and a vector boson, okay? We know how to coarse grain these theories. We know how to integrate, how to have cutoffs, okay? How to throw away the high frequencies in a quantum field. But what we don't know how to do is how to throw away the details of a theory for social systems. So this is just a clip from a recent paper that we're finishing on the dynamical structure of Wikipedia. So this is a model here. This is a Markov chain model for how the group as a whole decides whether or not to fight. These are these D states where people argue, okay, or cooperate. These are these C states, and occasionally you have a sort of intermediate phase. Okay, so this here is a theory just as much as that's a theory. Okay, if you're a physicist, you're probably not very impressed, right, because it's discrete. Okay, it's not continuous, right? If you're a string theorist, you think this is all wrong, right? Nature is fundamentally continuous. Okay, these theories are different, right? They also don't generalize as nicely, right? So this is the model for how people argue on the page associated with Barack Obama on Wikipedia, right? How people fight about what to put in. Okay, but this model here generalizes only in some ways to, for example, how people fight on the George Bush page, or how people fight on the page associated with global warming. One thing I'll tell you that does generalize is the spectral gap is very small, actually. The return to equilibrium is very slow. But we're still interested in how to coarse-grain these models, okay? How can we simplify a story like this, just as in the past we've been able to simplify a story about quantum fields or even classical fields? So not only are the theories different, the processes themselves different, okay, but the arena under which these processes unfold is distinct. So when we go to social systems, cognitive systems, biological systems, we go from these highly regular worlds here, okay, so this is just a discrete model, okay, of some three-dimensional space-time. Okay, we go from these highly regular worlds, right, so it might be discrete, might be some symmetry like SO31, right, Lorentz symmetry, okay, to spaces that are incredibly inhomogeneous, structured, variable from case to case, okay? And where the best models we have of this structure are in fact only probabilistic. We may only be able to describe this class of models by talking about the probabilities of certain network features, okay? Some of these structures here, so this is an interaction network for yeast, for the genes associated with the development of the little microorganism that makes beer. Okay? This structure here is probably not generalizable to other systems, in addition, of course, to being incredibly inhomogeneous. This space here, the physical space, looks the same everywhere. It's the Copernican principle. This space here has central nodes, right? It has peripheral nodes. It's incredibly inhomogeneous. You always know where you are in the yeast network, but you can get lost in the vastness of space. So if I zoom back, we have averaging processes, the question of how to take QED to larger and larger scales, smaller and smaller energies, right? And a similar question for how to coarse grain away the individual decision-making, for example, in arguing on Wikipedia. And we have a parallel problem, which is the averaging out of structures, okay? We know in some sense how to coarse grain this lattice. We might just take all the nearest neighbors and clump them into one big glob to make another lattice that's larger and has fewer nodes. Okay, just as we might, for example, want to simplify this network here. Okay. So averaging structure versus averaging processes. I would say that averaging structure, so this is another way to say averaging structure is to talk about clustering. Okay, and I would say that averaging structure, clustering a network is, I would say, known science. It's about finding ways to group nodes on the basis of some structural principle, right? So for example, I might give you some sort of massively complicated network like that yeast network, and you might have some algorithm that goes through and finds groups of nodes that are connected within each other, but have fewer connections outside. You might call that a cluster, right? So this is how people try to simplify networks. Okay. In fact, actually, there's a large number of algorithms for clustering networks. So if I just Google and Google Scholar network clustering, I'm not sure how reliable this is, but it gives you a sense. There's 11,000 hits in Google Scholar for how to cluster a network in 2014 alone. So people have talked a great deal about how to take a complex inhomogeneous structure, usually represented by a network, and coarse grain it down. Okay? Try to simplify that network into its essential components. What we don't know how to do, or at least we have much less knowledge about, is how to average the processes that occur in those spaces, on those networks. And that's what I'll talk to you about today. Outside, I should say, outside of the physical sciences. So in the physical sciences and renormalization, for example, that's how we average processes. That's how we simplify something like QED. Okay, and perhaps the reason we've been able to make progress in physics is that the parallel problem of how to simplify structure is obvious. We believe our theories are local, So the way we average out a lattice is just take nearest neighbors. But in the case where the system is complex, where the system is a cognitive network, a biological network, okay, we have very little idea. So what I'm going to talk to you today about is 3 stories about how to coarse grain, how to renormalize processes that are cognitive, biological, social processes that don't have the regular structures of a physical theory, that have far fewer constraints, for example. Okay? And I was told by my tutor I should give a colloquium, which means I don't only talk about my own research. And so I will attempt to put this in context. Of course, these are my own particular interests. If we have time at the end, and hopefully we will, I'll talk about coarse graining in the real world, and that will be our discussion of avian politics. So I'll talk first about Markov chains and something called a semigroup. So a Markov chain or Markovian process is pretty simple. You may have encountered it before. This is an example from Bill Press, who wrote a book called Numerical Recipes. And in the 3rd edition, he finally talks about biological systems. So a Markovian process is pretty simple. You have a set of states. They can be countably, uncountably infinite, but usually we talk about them as finite because we like to draw them. Okay? You have a set of states, okay, and you have transitions between these states. So this is an example of what Bill calls teen life, right? So I might be in the state eat, okay, and with a 10% probability, I'll transition to the state study, okay? But at the next step, with 100% probability, I will start hanging out, okay? And then maybe, 20% I'll go back to eating, right? 20% I'll go call someone on the phone, and I might stay there for a while, right? With 70% probability, some exponential decay here for how long I stay on the phone. Okay. So this is just a play example of how we might model a system, complicated system, right, such as your teenager. And the other thing Bill adds here is that we may not have direct knowledge of these underlying states. If you're a parent, okay, you may not know whether your teen is eating, okay, hanging out, or sleeping. Okay? And so, for example, he might emit one of these 5 behaviors with some probability based upon the state he's in, right? So, for example, if he's eating, okay, there's a 20% chance that while he's eating, he won't even reply to you when you yell his name, right? There's a 20% chance that when he's talking on the phone, he'll actually claim to be studying and so forth. So this is a Markov chain. This is how we might have only partial knowledge of the underlying states. And both of those concepts will become crucial in a second. What I'm going to tell you now is how to coarse grain this system. What coarse graining will amount to is saying, look, hanging out and sleeping are really not that different. They're pretty much the same. So if I wanted to have a simpler description of what my teenager was doing, I'm going to lump those into one bigger state. Okay? Or I might say, talking on the phone and studying, they're actually quite similar. So I'm going to lump those together. And if I did those 2 things, instead of having a model with 5 states, I would have a model with only 3. So one claim I'll make, and if you're a physicist, you might disagree, but I think it's a good analogy, if not a precise mathematical claim, is that Markov processes are the discrete time versions of local field theories. Okay? And so we're going to use them over and over again. The reason I say that is because whether or not you end up studying depends only upon what you've done in the previous time step. Okay? If you're eating, you have a 10% chance of transitioning to study. It doesn't matter what you were doing before you're eating. The system forgets. I don't have to go arbitrarily backwards in time. As long as I know the state I'm currently in, that tells me everything I need to know about what's going to happen next. So I'm going to tell you how to coarse grain these theories. I'm going to start with a very simple case. I'm going to throw out all of the stochasticity in a Markov process. And if I do that, I get something that might be familiar. I get something called either a group or a semigroup. So I'll talk about the group case first. So does anyone not know? I should ask this. Raise your hand if you know what a group is. Okay, excellent. Nobody has failed to raise their hand. So I'm going to show you a very simple group. This is the permutation group on 3 symbols, right? It's not like a very impressive Lie group that you guys, I'm sure, hang out with all the time, okay? So a symmetry group on 3 symbols has 8 possible, what we call states. We'll call them states. And what I've done here is write down 2 potential generators of this group, okay, R and S. And I used to do this out. I think Matteo might have seen me do this when he was a summer school student. Okay, so R here. So I'll start with the the state 1, 2, 3 at the top, you might imagine those as 3 cards, right? So R, what I'll do with the R state, or the R generator, is I'll just take the card at the bottom and put it on the top, okay? And I can do that again, right, and again. And if I do that, I cycle through these 3 states in the group, okay? My other operation here is S, the swaps. That just means I swap the top 2, okay? So I have 2 operators. I have 2 ways to transition from these states. And you can think about these as analogous to the states in the Markov chain I just showed you, right? This is, this has far fewer cool stories associated with it, right? This is not hanging out or talking on the phone, but you should think about it in exactly the same way, okay? So given some input from the environment, an R or an S, the system will transition between these states, okay? So I'm going to show you something very simple, your first example of how to coarse grain a process. Okay, and this will test your mathematical knowledge. What I can do is say, you know what? I don't really care about the difference between these 3 states. Okay? For me, 1, 2, 3, 3, 1, 2, and 2, 3, 1 are all equivalent to each other. I'm going to ignore any differences they might have, any perceptual differences if I'm using this to model a real-world system. Okay? And I'm going to do the same thing with these 3 states here. And if I do that, all of a sudden, a really complicated model turns into a much simpler one. Okay, before I had 6 states and some complicated pattern of transitions. Now I only have 2 states. Okay, the S operator takes me between them, and the R operator is the identity. Okay, so I've taken this larger system and I've coarse-grained it down to a much simpler system with far fewer underlying states. And if I do this, okay, this is the world's simplest group, right? This is a 2 counter. Counts to 2, right? 1, 2, and then it runs out, so it goes back to 1, it resets. One thing I also want you to know, and this will come back in a second, is the action of this operator here, if I go back to the fine-grained system, modulates the action of the R. So if I'm on this side, R cycles me like this, okay? But if I hit the S button, okay, the direction I cycle goes the other way. So at the top level, I have a 2 counter. Okay? That 2 counter feeds down to influence the microstructural details of the system. Okay? And so this is what we call a hierarchical decomposition. Okay? So at the top level of this system, it's a 2 counter. Okay? So if you get an S, go from A to B, or B to A. Okay? If you get an R, ignore it. Just stay in the same state. Okay? Below that, at some finer grain level, I now have a little submachine. A little submachine actually counts to 3. Okay? And I transition between these states with the letter R. So if I get an R, the top level machine ignores it. Says, look, I'm too simple. I don't even know what an R means. Forget it. I don't even know what it means. Okay? It passes it down to the lower level system here. Okay, and that lower level system interprets the R, and it will cycle through the states, but in fact, it will depend upon whether the higher level system is in state A or B. If it's in state A, in fact, it cycles this way, and if it's in state B, it cycles that way. Okay? So what I have told you in a very picturesque and sort of, BBC television series is something you know very well. It's the Jordan-Holder decomposition. Okay? S3, okay, it's just the semi-direct product of Z3, that's that lower level counter here, and Z2, that higher level counter. Okay? Jordan-Holder decomposition known since the 19th century. Okay? And it says, in fact, any group can be decomposed into this long string of simple groups. And in fact, now there's this big atlas that you can buy. It's not a road atlas, but it sort of looks like one. So when I was taking this out of the library, the janitor asked me if I was going on a trip. I was going on a trip into mathematical land, right? And here's just another example. This is how to factor something even simpler than S3. Okay, this is the 4 counter. Okay, so if I do the Jordan-Holder decomposition on a machine that counts to 4, Z4, it factors into 2 prime groups, a top-level counter and a bottom counter, where the transitions are defined by the state of the top-level counter. So all the Jordan-Holder decomposition tells me is that I can represent a system with 4 possible states as a binary number, 0, 0, 0, 1, 1, 0, 1, 1. And the transitions between these 3 states actually decompose into a lower and a higher significant bit. Okay. A group is a reversible system, right? For any action, for any element of the group, there exists another element of the group that undoes it. Everything has an inverse, okay? And so the product of R and R inverse is the identity. R inverse has some phrasing in the group. In fact, in this case, R inverse is just R squared. But what happens if your Markov chain has some irreversibility? What happens if you get driven over time into a subspace that you can't get out of? Okay? Now that group is no longer a group, it's something called a semi-group. Okay? So this should be pretty clear, but if you have like an iPad or an iPhone, right, and you panic, you've done something wrong, you just hit that button on the bottom, right, and it just foops you back to the home screen, right? It's an irreversible computation, right? There's no way to get back out. Okay? There's no way to tell which program you were in before you hit the button. Okay? So your iPhone is a semi-group, just in case you were wondering. It turns out, and this wasn't proven until the 1960s, that you can do a similar decomposition to the Jordan-Holder decomposition even if the group is a semi-group, even if there are irreversible operations in the group. So this is called the Krohn-Rhodes theorem. Krohn and Rhodes are two mathematicians. They actually proved this together for their PhD dissertation. Rhodes became a mathematician at Berkeley, and he's still a very charismatic guy. He's a little strange. He wrote a book about how the Krohn-Rhodes decomposition is everything in the world, that everything you can, I mean, like chapter 1 is like the Jordan-Holder decomposition, chapter 2 is the Krohn-Rhodes theorem, chapter 8 is like psychology, right? Okay. So Rhodes is kind of nuts, but Krohn was even more nuts, and he ended up in jail for kidnapping. So he became a lawyer. I think that's what happened. So the Krohn-Rhodes decomposition allows you to do the same kind of trick here, okay, but on an arbitrary machine. So this is an example from our paper. This is a paper in 2011 when I first became obsessed with this. Okay, so here's a little group. It's actually a semi-group. And one way you know it's a semi-group is that there's a little subspace here. There's a little subspace here, okay, that you can get trapped in, right? So if I start in that A state up there, big A, and I go and I hit it with a little a, then I hit it with a little b, I can never get back to A. I get stuck in that little oscillating subgroup there. So this is an irreversible process, or at least it has a little core of irreversibility. Eventually you get stuck there. But the nice thing about the Krohn-Rhodes theorem is it doesn't matter. I can do the same thing I did in Jordan-Holder, and what I've shown you here is how to coarse-grain this system into this much smaller system here. And I've labeled these states in terms of, in terms of the microstates they represent. Interestingly, this is if I just run the Krohn-Rhodes algorithm, there's a little bit of code you can do. Rhodes's great grad student developed this code, so you can actually run it yourself if you have an arbitrary semigroup. And this is just what comes out of that top level of the hierarchy here. This is the top level sort of smoothed machine. Yes?
When is this decomposition unique?
That's a great question. So it's not, there are some constraints on it, but there's a lot of flex, right? So for example, I did the decomposition of S3. You're a smart guy, right? Did the decomposition of S3. I could have done it the other way just by identifying the state slightly differently, right? So the decomposition is not entirely unique. One thing I should say is that there are constraints. So you have to add, basically, Krohn-Rhodes says, all the simple groups, you need all the simple groups, you need one other kind of bizarre group, which is the pure reset. So a semi-group that is, in fact, it just, on being hit with a letter, takes everything to one state. So with that additional tool in your alphabet, okay, you can do this decomposition. Somewhere down here, you'll have a state, for example, that looks like this. Okay? So there's a couple things. The number of these is fixed, and I believe the number of groups within is fixed, but the order is not. And you can also take a chunk and put it down, right? A chunk of groups bookended by these irreversible operations. So there's a lot of flex, right? Generally, if you have an algorithm, it will tend to find one, but if you run it twice, in some cases, because the algorithms can be stochastic, they have some seed, you'll get a different one. Okay. So this is a very simple thing, right? I've taken this group, or semi-group, and simplified it. I've coarse-grained the process, right? I've tossed out microphysical details, and notice that, for example, A and H are identified here. A is in no real sense a neighbor of H graph theoretically, right? So if you use like a network clustering algorithm, there's no way the system would realize that A and H are actually quite similar. They play a similar role. So another example, I think, of why, if you want to do cool stuff in coarse graining of complex systems, forget network clustering, right? Because the process itself is much more interesting. And the graph theoretic structure, right, you might say, look, if we did a network clustering on this, you'd say, like, look, A, B, and D are clearly related. But in fact, A, B, and D are the two main, or the three symbols that distinguish the upper level states. So you can get obsessed by this, and people do. So here's like a Chrome rows decomposition of some massive game, right? We played with this for a long time. There are good things and bad things, right? The strength of Chrome rows is that it's deterministic up to these symmetries, right? Up to these degeneracies. It's exact, right? And we'll talk exactly what that means. But this thing here preserves all the structure of this that it contains. It doesn't violate, this doesn't violate any of the transition rules here once you know how these states coarse-grain. Okay? Just in the same way that this here preserves all the rules of S3. Okay? Or rather, it preserves all the rules it wants to. It doesn't violate anything. Okay? So it's exact. And we also have known algorithms for how to do it. Okay? The weakness is clear to me, and I'll just tell you what it is. Right? The weakness is that this top-level state, okay, yeah, it's the top level of some coarse graining, but it's not necessarily the most important. Okay? It's not necessarily the thing you might care about at the highest level, the thing that you want to get out from simplifying the system. Okay? And so I mentioned, for example, that there's this little irreducible subspace here that everyone eventually gets sucked into in this semigroup. Right? Eventually, you get hit with enough letters, I'm stuck, right? Okay? And so maybe you think that's the most important thing, in which case you might want to approximate that group, okay, by some kind of stochastic system like this one here, where basically you spend some time on the perimeter, okay, but eventually, right, some B takes you to that little irreducible subspace here. So the Coarse-graining theorem has advantages, but I think in the end, okay, and this would be, of course, non-deterministic. Notice that B may take you within or push you out, right? So this is clearly now an approximation. This is no longer a group in the standard sense, in the way that this is. Okay. And so I think we have to go beyond the Chrome roads. Chrome roads, I think, is an example of how to coarse-grain a process, to show that coarse-graining a process is a non-trivial thing. What I'm going to talk to you now about is a paper that we just came out with on what we call state space compression. So this is a framework for describing what it would mean to coarse-grain a process more generally. What Chrome roads does is take a semigroup, okay, and show you how to find smaller semigroups that it decomposes into. Okay? State space compression is a more general process, okay, a more general process that includes Chrome roads as a special case. Okay, so here's what you have, right? You begin with your microstate dynamics, your full fundamental theory of everything. Okay, so already we're different from renormalization, right? Okay. You have constraints. These constraints are constraints on what you can do as a theorist, as an observer. You might have memory constraints or computation cost constraints. So you can't actually simulate or model the full microstate dynamics. Okay. This constraint, these set of constraints, forces some kind of coarse graining of the microstate, some kind of destruction of information. You also have an observable of interest, and so this is where we diverge from Chrome roads. There's something you care about in the system. Okay? So for example, say you're trying to coarse grain the icing model, right? What you might care about is getting the average magnetization right, and so we also have to specify a penalty function, which is how bad it hurts when we get it wrong. So with these four specifications, okay, I tell you what the fundamental theory is. Okay? I tell you what my constraints are, how much I want to simplify it, or how much I need to simplify it. And then I tell you what I care about. Okay? And I tell you how much it hurts when I get it wrong. Okay? And so given that, I have three levels of my system. I have my microstate, which I'll call eta. Okay? But my constraints mean that I have to somehow coarse grain or throw out some of the details of the microstate. I'll call that the compressed state, eta bar. And I throw this stuff out, I get this, and I want to predict some observable eta hat. Okay? Now, if you're really screwed, right, the compressed and observable states might be identical. Those two spaces might be identical. But in the general case, you might be able to keep track of more things, okay, than you actually care about in the end. But the reason you keep track of them is because it helps you simulate the dynamics of the observable. Okay? So here are three pathways for understanding a system. Let's start with B here. Okay? B is what we call optimal forward prediction. Okay, I know the microstate, I know the dynamics over time. So eta goes to eta prime in one time step. Okay, and then from eta prime, I could just go all the way up quickly and tell you what the observable is going to be at the next time step. Okay, so this is just optimal. This is no coarse graining, not throwing anything out at all. Okay, here's pathway C. Okay, what I do is I coarse grain the microstate to my compressed state. I have a theory, a coarse-grained theory of how the compressed state evolves. Okay, so I get this one here, and now I can predict the observable I care about, but I'll do a noisier prediction than I would be able to if I was using the full microstate. Okay, I'm going to get this here wrong if I take this path. I'll get it slightly wrong perhaps, but I'll get it wrong if I take this path versus taking this path. And then finally, you can see A here, right, which is if I just go all the way up to the observable and try to simulate its dynamics alone. So in the Ising model case, that would be like trying to come up with a differential equation for magnetization as a function of time. Okay. So this should be very clear and similar to the example of renormalization in physics, right? I have some microstate, which I coarse grain to some larger scale, to some mesoscopic scale. Okay? I might average, in the physics case, spatially. And what I do, and what I get right out the other side, is if this is my fundamental theorem governed by some Hamiltonian, okay, eventually that theory changes. It flows, okay, to some other theory. And in this case, I've neglected the higher order terms, which I'm sure you know are there. But the underlying parameters of the model will change. What's nice about the renormalization case is that the model actually retains the same form. You can still do all your quantum field theory tricks still work when you coarse grain, when you renormalize a field. So I'm going to walk you through a simple example of a more general system. What we do here is coarse grain the Ising model on a complex network. Okay? It's actually a ferromagnetic interaction, not a spin glass, and I'll show you why we do the ferromagnetic case in a second. But I'm going to just set up a simple discrete model. And so, okay, this is some complicated Lagrangian action. I'm going to do a discrete case here, okay, where I have nodes, sigma I, also labeled by time. These nodes interact in space, and they also interact from one time step to the next. And this means that I can have some probability for all paths through the system, which I write like this. My exponential of this action, okay, there's no h bar because we're making this up as we go along, okay? But I can get some probability for all possible paths through the system, okay? This is nice if you're somebody who does simulations. In fact, what we have here is a full space-time action, okay? This is not some sort of spatial action with some simulation, some Metropolis Hastings simulation on top. So it allows us to do nicer work. For example, to quickly decompose that action into the product of time steps, okay? Where instead of considering the nodes linked together at a constant spatial slice, we have nodes that link together, okay, from one time to the next. So the state of these two neighbor nodes here influences the third node at the next time step. Okay. So this is a Markovian dynamic, called local field theory, right? So the probability of being in configuration eta prime, microstate given eta, is just some exponential of this nice pair, of this nice pairwise interaction between eta at one time step and eta at the next time step. Okay, so we're just setting up my dynamics here. So coarse graining, I might have two configurations in a particular time slice, eta 1 and eta 2. Okay, so these are distinguishable, notice, because they differ in the value of their first node. But we'll call them equivalent states if we trace over the first node. Okay, and what that means is we now have some new coarse grain configuration eta hat, which can't tell the difference between eta 1 and eta 2. Okay, so this is very, very similar to what Leo Kadanoff called decimation, okay, where we toss out some information in the system. But notice that in Kadanoff's case, we throw out the states of nodes that are nearby. So we maybe have a block of 5 nodes, and I'll say, look, I'm just going to care about the value of this one and neglect the guys nearby. That's how I'm going to renormalize. Here, we have yet to define how we're going to build these equivalence classes. There's something very nice, and again, this is something that has a parallel in the field theoretic case, right? My underlying dynamic for the microstates is Markovian. Okay, the probability of being in some configuration at the next time step is conditional only upon the current state that I'm in. Learning something about the distant past has no influence on what's going to happen next. Okay, so this is exactly a Markovian dynamic. It's a very local theory. But once I go to the coarse-grained state, this no longer holds true. So for example, I might want to talk about the evolution of this coarse-grained state from time t to time t plus 1. Okay? So one thing I can do is write down this term here, which is easy. I can write down this one because I know the microstate case, and I just sum over all the elements of the equivalence class. But then I have to know what's the probability of being in a certain microstate right now. So one thing I can do is say, OK, look, given the equivalence class I'm in, I know what equivalence class I'm in. So what's the probability of being in any particular microstate of that equivalence class? OK, so that's one way I can write down this Markovian dynamic. OK? The problem is that I can get a better approximation to this transition probability if I go further back in time. In fact, this rule here no longer holds once I go to the coarse-grained states. Coarse-graining introduces non-locality. Okay, non-locality in time. So in case this is not entirely clear, I like to think about it this way. Say my observable is the total spin of my Ising model positive or negative. Okay, so here's one time series, right? Okay, so I'm trying to predict what's going to happen next. This was the time before. In this case, it's been plus for a very long time. So what's the probability that it'll be plus in this time step? Probably pretty high. Okay. Here's another system, right? Another time series. And notice that they have the same recent past, but they differ in the long time past. Okay? And now I have this sense, okay, in this one, my system was probably frozen in. It's just stuck in some local minima. Everybody's positive, some ferromagnetic interaction. Okay, but in time series 2, it feels like it was probably fluctuating. It probably wasn't quite frozen in yet. And so my guess about what's going to happen next here is different from my guess about what's going to happen next here, even though the step before was identical. Okay, so this is just an understanding of why coarse-graining means non-local in time. Okay. And in fact, generically, arbitrarily far back in time. I always gain by increasing the number of past time steps that I use. And so that means, for example, if I try to build a Markovian process out of my coarse-grained system, my Markovian process usually has an infinite number of states. Notice, interestingly, that there is no emergent non-locality when I do the Krohn-Rhodes theorem. This is my coarse-grained system, right? It's also Markovian, okay? What happens when I hit this state with an A doesn't depend upon where I came from. So the Krohn-Rhodes theorem actually precisely nails, okay, the local coarse-graining. But an arbitrary coarse-graining, and this is the intuition, arbitrary coarse-graining will induce correlations arbitrarily far back in time, okay? And they don't necessarily die out the way you'd want them to die out. So I specified the microphysics. I've talked a little bit about what the macro or the mesoscopic dynamics are going to be. They're no longer Markovian. They're nonlinear, or sorry, they're non-local. Okay. And by the way, this is what happens when you coarse-grain a field theory and you start getting these higher derivative terms. The higher derivative terms were essentially doing a Taylor series approximation of the field arbitrarily backwards in time. Okay. So that's how it shows up in a very brief narrative account. The parallel story shows up when you coarse-grain a local field theory. You start getting all these higher derivative terms. They don't make the system unstable. Okay. So this is my dynamics of my renormalized states, or this is the microphysical dynamics. I'm going to make a little approximation, and what I'm going to show you next, which is I'm going to say, look, the microstates thermalize. Okay. So when I'm in some macro state, particular kind of macro state, then the distribution within that macro state is thermal. Okay, it's an equilibrium. So I'm forcing it to be Markovian. Why? Because I have limited time in my life, right? Okay. So I got one last thing to tell you, or rather two last things, what I care about and how much it hurts when I get it wrong. And so I'm going to use this thing. It's an accuracy cost. It's an information theoretic accuracy cost. Okay. What I want to do is I want to predict the renormalized model, the coarse-grained model, as well as I can. I want the probability distribution that I believe about what's going to happen to the coarse-grained variable to be as close as possible to the probability distribution that I would get from the microstate reasoning. Okay? And so I use this thing called KL divergence. It's an information theoretic quantity about how distinguishable one distribution is from another. It cashes out literally in a sort of Bayesian fashion as saying, look, I start getting samples from one distribution. How quickly do I accumulate evidence for the fact that this distribution is actually a little bit wrong? That's what the KL divergence is. Here are my two terms, right? This is the optimal prediction I can do, okay? And this is my lossy prediction, okay? This is the true microstate dynamics, okay? And this is the microstate dynamics I'm forced to use because I have to operate on this coarse-grained scale, okay? So I'm going to plot you now the penalties this accuracy cost, okay, as a function of underlying temperature in the icing model, okay? And so here's beta, inverse temperature, okay? And here's how the accuracy cost rises and falls as beta goes from the high temperature limit to the low temperature limit. And these two limits are, in fact, very different. Notice that somewhere around here, which is in the phase transition region, okay, the accuracy cost peaks. So this is just a simulation, right? Presumably, as this system gets closer and it gets larger and larger, this sharpens up, but we haven't done the finite scaling. So at the high temperature case, or sorry, at the low temperature case when beta is very large, okay, the system is highly ordered. And what that means is the equivalence classes are really predictive. My equivalence class might be, okay, look, just take every third node, is it positive? Okay? And if the system is frozen, just knowing one or two nodes actually tells you everything that's going to happen next, because the system is basically stuck. It's not going to fluctuate out. On the flip side, in a highly disordered state, microscopic knowledge is just as bad as macroscopic knowledge. Okay? So there's no coarse graining I can find that's useful because there's no fine-grained theory that's useful. The system is totally random, uncorrelated from time to time. I should say here, this is the optimal coarse grading. So we look at all possible equivalence classes for that particular icing model. Okay. So I should say this is, if you're a complex systems person, you always care about, can I measure complexity, right? And so this is the humpology, right? The zeroth law of complexity is that somehow the thing you care about should be a hump, right? When the system is random or totally ordered, it's low, and somewhere in the middle, it's high. So here's the coda, right? So we have a fine-grained microdynamics. We care about a coarse-grained macrodynamics. And we have the computational power to track only in the mesoscopic regime. Okay. These are the pathways that we can take. What I showed you there, the solid line, was if I went all the way up to the observable I cared about, okay, and predicted forward. There's a dashed line that has a lower accuracy penalty where I go to some compressed mesoscopic regime. And so, in fact, I can do better predicting this observable because I can simulate more of the fine-grained structure of the system. So I'm trying to think if I should skip this and go to the birds or not. Do you want to learn information theory or do you want to hear about birds? Both. OK. I'll talk about this briefly. It's beautiful work. This is work not done by myself, so I can praise it to the skies. It's by a woman called Sarah Marsden, who's a graduate student at UC Berkeley, who you should email and tell her not to leave academia, because I love this work so much. But she's thinking about it. And then Jim Crutchfield, who is one of the great figures at the Santa Fe Institute. He's been around for many years, and developed a theory of what we call causal states in collaboration with another great figure at the Institute, Cosmo Shalizi. So causal states is a story about what a time series means and how to predict it going forward. So I'll define a variable x. And x, at some particular time, is the full history of everything that's happened in the universe, or everything that happened in the time series you care about. Okay? So I'll use eta for a time slice microstate as before. So this is, eta just before, eta 2 steps before, eta 3 steps before, and so forth, going all the way back. Right? Okay. And then I have the future, everything that could happen in the future, right? So this is a list of what's going to happen next, and 1 step, 2 steps, and so forth afterwards. Okay. I have some conditional probability what's going to happen in the future conditional upon what's going to happen in the past. It might be totally deterministic, right? It might be stochastic for some reason or another, whether you believe in fundamental randomness or whether X is actually not the full story of the universe, but just, for example, the financial time series you're interested in. And what we're going to do is find a function f that maps all possible histories into a smaller space, potentially smaller space. And it's going to do that in a really clever way so that the conditional probability of the future given the past is equal to the conditional probability of the future given this coarse graining on x, on all the full microstates. And this f of x defines what we call the causal states. Okay? The causal states of the universe is not, the causal state of the universe is not a description of everything that's happened. It's a description of everything that's happened that matters for what's going to happen next. Okay? Causal states throw out all of the totally irrelevant information. Okay? They throw out the stuff that doesn't matter at all, and they keep everything that does. Okay? Because what you want is you want this f of x, okay, to be exactly equal to the full conditional probability. So causal states are in some sense a compression. They're in some sense a coarse graining, but they don't actually hurt, right? There's no penalty. You're just throwing out the stuff that's irrelevant. For example, if it's a Markovian process, you can throw out everything except the last time step. Okay? But if the process is hidden Markovian, okay, it usually implies that f of x, the set of all causal states, is countably infinite, at the very least, if the system is discrete. So Jim thought about this, and Jim and Cosmos thought about this, wrote a paper on something called the information bottleneck, because they were interested in getting better, or rather smaller sets than the full set of causal states. So what they wanted to do was throw out, coarse-grain, the causal states into a smaller set of states. And if they do that, by definition, they're going to screw up the probability distribution. But the goal is don't screw it up too badly, right? Or at least have a little knob that you can turn that says, look, I'm going to throw out more and more states as I turn this knob, and I'm going to throw them out in the cleverest possible way. Okay? That's the intuition behind what they were thinking about. And so Jim and Sarah this year, the preprints on the archive on December 9th, okay, actually wrote down the full story. So in order to tell you that, I'm going to have to tell you what the information bottleneck is. I told you what causal states are. What they're going to do is apply this theory, called the information bottleneck, to throw out, to lossily compress, like a JPEG, right? Throw out information about the causal state, but so it doesn't hurt too bad. So the information bottleneck was a story actually written just about the same time, okay, that Jim was thinking about the same problem. Okay? And so I want to tell you a little story, the information theoretic story, and then I'll tie it right back into causal states. Okay? So here's the story originally that Charlie Tishby and Bill Bialik, and I don't know this gentleman or lady here. But the problem is this. You have some source and you have some receiver. Okay? And X predicts something about Y. Okay? So if you keep track of X, you'll do the best at predicting Y. Okay? But one question you might have is, how can we code X efficiently so that we can predict Y? And in fact, how can we code it using some code book that's lossy? Okay? So I'm not going to keep all of the information in the source. I'm not going to keep all of the fine-grained information here. I'm going to throw some of it out, okay, using this code book. And then the symbols of the code book are going to be used to reconstruct Y. Okay? So instead of going this full pathway here, I'm going to go through this. Information gets lost here. Foomf, 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 right? Okay, so this is a lossy compression of the source. So how do I do this? Well, I have to tell you what symbols I'm going to emit from my code book conditional upon the X, right? This is my little encoder that takes the really big system and coarse-grains it into this smaller code book, okay? And what I'm going to do, at least what the information bottleneck method tells me to do, is the following. It says, look, okay, over all possible probability distributions, minimize this quantity here. Okay, so I'll explain it, right? You want to make this small. This is the mutual information, so time it. Can you raise your hand if you know what mutual information is? Fewer people than know who groups are. Okay, so mutual information is how much does knowing the value of one variable reduce the uncertainty of knowing the other? Okay, so I have some entropy. How much does that entropy go down if I know the value of a second variable? If they're correlated, once I know something about the other variable, I'll know something about the first one. Okay? So, like, I don't know, if Matteo and I exchange information, if we're coupled in some way, and if he's happy, I'm happy, then you're less uncertain about my mood if you know his mood, on average. All right? So we're going to minimize the mutual information between the code book and the source, which seems a little paradoxical. But what this says is minimize this to throw out as much of X as you can. Okay? Throw out as much of X as you can in the code book, but don't do it so badly that you decorrelate with Y. Okay? So throw out as much as you can of X, okay, but make this as large as possible. Okay? And that beta parameter is Lagrange multiplier, and that's the knob you turn. Okay? So if beta goes to infinity, if it gets really large, it says, don't worry about this term. Just maximize the mutual information between T and Y, okay, given this output probability. In that case, just go to the causal states, right? You have infinite resources, who cares, right? As beta is finite, okay, it starts saying, you know, I really want to throw out some of the information about X. It becomes lossy, okay? And interestingly, with this penalty function here, this actually is the same penalty function we use that I told you about in the Ising model case. I'm going to minimize the average KL divergence, okay? So let me summarize. Here's the past history of your time series. That maps to some lossy causal state. This state T, I just said, oh, it's T12 this time, right? This state T contains a lot of the information about what matters here, but not all of it, okay? that state T predicts the future pretty well, not great, potentially, but pretty well. And depending on how you set beta, this probability distribution here will be closer and closer to the full probability distribution where you condition on the causal states, or equivalently, you condition on the entire past. Okay? So that's how it looks in the microstate case. If you look at the coarse-grained dynamic, I just evolve over a much smaller set, okay, of these lossy causal states. This is our coarse-grained theory, and in fact, it ends up being, in this case, a Markov process. Okay? It could potentially be an infinite one, depending on how you set that beta num. Okay. So, summary so far, and then we have a little time for the birds. Okay. So, I told you about the Krohn-Rose theorem. The Krohn-Rose theorem was a way to coarse-grain semigroups. It's a lot of fun, right? And it has some nice properties, but in the end, the problem I think we have with the Krohn-Rose theorem as a way to coarse-grain computation is that it doesn't really make a distinction between what's important and what's unimportant. Okay? For example, in the case of coarse-graining S3, I could coarse-grain to 2 states at the top or 3 states at the top. Okay? I'd have to do a slightly different set of equivalence classes. But of course, the problem with Krohn-Rose, it doesn't say which one is more important. There's too much degeneracy in that story. Okay? Then I told you about something called state space compression, which is a framework that some of us worked together with on at the Santa Fe Institute. And so that was people who are both physicists, but also people interested in biological prediction. Okay? And state space compression, you can think of, one way to think of it is supplementing the Krohn-Rose with some idea of penalty function, a thing you care about. Okay? I told you about this work that's very closely connected that just came out, okay, on using the information bottleneck to coarse-grain causal states. I told you a little bit about these great things called causal states, what they were, and I told you how Jim and Sarah, or Sarah and Jim, used the information bottleneck to to lossily compress these causal states. Okay? So this group here also has a penalty function. And in fact, it was the same penalty function that I chose. State space compression says you can have different ones, right? But they chose one that I think is quite elegant, and something like, I mean, it's not a surprise that there are 2 physicists doing this, right? So finally, I'm going to tell you a little story. Okay, so this is like all the stuff that might be useful to you, right? But I'm going to tell you something that's really fun, okay, which is about how coarse-grained quantities play out in social systems. Okay. So now I get to have a little fun. So in 2008, I was really interested in things like back reaction. Does anybody remember back reaction? Are there cosmologists in the room? Okay, so back reaction was like, you know, somehow the really large-scale gravitational field was like going to back react. Okay, and so you get this, maybe you get some fictional dark energy, and the story, there's some apparent dark energy effects without there really being dark energy. And the idea was somehow, and I never quite figured it out, even though we tried to simulate it over and over, like the idea was somehow that the large scales could influence the small scales. Okay? That somehow you would get downwards causation. So instead of thinking of the microphysics influencing the macrophysics, okay, the coarse-grained state, somehow that loop would go backwards. That's all I got out of it. I never could write a paper on it. Okay? And I think, like, Niayesh showed it wasn't true, I think. It's an awful thing to say, but I'm no longer in cosmology, so I'll never have cosmologists as a referee. But closing that loop, the claim is, closing that loop actually happens in social systems. And why? Because we ourselves, we participate in social systems. We build coarse-grained models of what's going to happen, and we use that information to change our microphysical dynamics, right? We close the loop, right? Electrons don't really care about the overall magnetization of the solid, except in as much as it's mediated by their neighbors. Okay, but we as perceiving beings actually go and build theories. And in fact, when we build theories of politics, what do, right? We try to make them predictive. We care about predicting certain things, okay? And then we make decisions based on those predictions, okay? So individuals, so I'll draw a little feedback diagram here, right? Individuals take action in the world. We do things. We write blog posts. We vote, right? We're friendly or not friendly to people, okay? We're, I don't know, racist or not racist, right? And those actions create some kind of set of group-level social facts, right? These simply coarse-grain over the individual actions. They summarize the full dynamics of the system, right? So this is a story that you might well have told about how to coarse-grain or renormalize a field theory, right? Okay, I have the microphysical dynamics, okay? These lead to some kind of coarse-grained system with a particular set of dynamics that summarizes what goes along below, okay? Lossy compression. But what happens in a social system, okay, is that those group-level social facts actually feed backwards. Group-level social facts alter individual mental states. They change what we believe. And because they change what we believe, they change how we act. Okay? So that coarse-grained state of the system that we observe, we build theories about, okay, actually comes to alter what we believe about the world, changes our actions, and so in fact feeds back in. Okay? So this is an essentially cognitive part of the loop that I would claim is perhaps inaccessible in physical systems. But when your system gets complicated enough, perhaps when it's an evolutionary system that's trying to predict this in order to survive, right, it can't predict all the individual actions. It has to go to the coarse-grained level because it's not too smart like us, right? We can't imagine the whole world. Right? We can't build theories about politics based on every single American and Canadian in the world. Okay. Instead, we have to use these coarse-grained facts, but they influence what we do. Okay. And so I'll show you an example. I'll show you an example of this. This is work that Elizabeth Hobson and I did. Liz is a biologist, right? She studies birds. She studies the social systems of birds. And interestingly enough, one of the most coarse-grained variables for humans, I would say, or I would claim, is power. Okay? When I walk into a new environment, like I walk into PI, right, I'm probably going to try and figure out who runs this place. Right? How am I going to get food, right? Who can throw me out? Who do I have to be nice to? Who do I have to be good to? I'm good to everybody. I try to be nice to everybody, right? But in most cases, we try to model the power structures. We try to figure out, okay, who's an undergrad? Because you don't want to treat an undergrad like a professor, and you certainly don't want to treat a professor like an undergrad. So we're constantly trying to build theories of where the power is in our system, okay? If you're a Quaker or something, okay, maybe you don't. But other people certainly do. It turns out, in fact, that birds do the same thing, okay? There's something called a dominance hierarchy in animal systems. In fact, in a wide variety of animal systems, you may have heard it called the pecking order. That's because it was first observed in chickens. Okay? Monk parakeets don't peck each other. They kind of whap each other off the branch. And it's unclear why they're doing that, right? Because these guys, this is in a captive group. They're not in cages. They're in a sort of big pen, so Liz can observe them. Okay? They just kind of knock each other about. Okay? So those microphysical facts about the system are who's bumping who. Okay? So this takes about a second. I should say, by the way, has anybody been to UChicago? Okay, so UChicago, monk parakeets grew up and they come from Chile, but they're kept as pets, and they escape, and they're really good at forming societies. And so in fact, even though they're from Chile, they live around UChicago. They build these colonies. They're really good at society, and that's one of the reasons why we can use them to test theories about societies, because they're super social. Right? They peck each other all the time. And in fact, not only do they peck each other, right, but those pecks coarse-grain into a dominance hierarchy. So we take the individual actions. So Liz, I mean, this is great, right? Think about the LHC, right? But imagine doing it by hand, right? So what Liz did for her PhD thesis was sit there and watch all the birds and count how many times one bird pecked another, okay, over the course of a month, okay? It's amazing. And there's n by n actions. In fact, it's n by n minus 1 because a bird tends not to peck itself. Okay? There's no self-harm in this system, right? So that's a huge, right? It's a huge number of interactions. The dominance hierarchy coarse-grains all those into n power scores. Okay? So what biologists or animal behavior people try to do sometimes is figure out how these microphysical, obviously they don't use the word microphysical, right? How these microphysical dynamics coarse-grain upwards into a power structure. Okay? And it's a little more complicated than you might think. The bird who pecks the most is not necessarily the bird who has the most power in the system. And one of the sort of ways people like to do this is, I won't tell you its page rank, I'll just tell you it's the first eigenvector of the system, right? Take the stochastic matrix that describes the flow of aggression. Take the first eigenvalue, it's 1. And the eigenvector associated with that is the stationary distribution of who's getting beat up. Okay? And the person with the highest probability of being found to be aggressed against has the lowest power, and so forth down the line. So what that means, for example, is that, yeah, it's not great to be pecked by somebody, but it's even worse to be pecked by somebody who himself gets pecked by somebody. Okay? So this is great, right? Eigenvector centrality, it's also called. Before there was this, they invented something called David's score, which is like the two-step approximation to the first eigenvector. Okay? And so what we can do now is build a model of the power in the system. I'm going to show you a null model associated with it, because what I'm going to show you is how, over time, the microphysical dynamics come to be influenced by the power. So what's going to happen is actions, microphysical actions, create a power structure. But over time, that power structure feeds back to influence the actions. And so what I have to show you is what the world looks like without that feedback loop, okay? So the compression is defined, right? Many microhistories are compatible with the same overall power distribution, right? There's many ways. There's M by N is larger than N, right? There's many different pecking structures, pecking histories that lead to the same power. So what we're going to do is we're going to sample uniformly from that whole range of microphysical dynamics, right? We're going to pick at random, right, political histories of the bird that Liz observed. Okay, we're going to pick them at random. Okay, and we're going to compare them to what we observe. And so here's what happens in week 1 of colony formation, right? So Liz, this is great, right? So for her dissertation, she released the birds into the pen. So this is the first time. It's not the first time they've all met each other, but it's the first time they've all interacted together in a society. Because this is week 1. Blue is the null, red is the observed, okay? And what I've shown you on the x-axis is the rank difference, and on the y-axis, the average aggression directed. Okay? So what you can see is this curve goes up. In fact, both curves go up, which means that you're more likely to peck or displace somebody who's further down from you in power. Okay? And vice versa, you very rarely peck somebody like 10 steps higher than you in the hierarchy. Okay? So this is week 1, right? Or say quarter 1 of the system. Okay? So red, observed aggression. Right? The null is the dashed line in the blue, right? It's the same power score as arbitrary aggression, right? So pick randomly from the equivalence class of aggression histories. Okay? This is great, right? So here's what happens on week 2. Right? And here's what happens on week 3. What the birds are doing is learning to focus their aggression towards those nearby them in rank. Okay? The microhistories that coarse-grain into the power structure become increasingly unusual, increasingly strange. As the birds use, at least our claim is, as the birds use their knowledge of the coarse-grained variable power to decide what to do next. The only way, we believe, and this requires more tests, right? But the only way they could be doing this is if they were using facts about power to decide what to do next, okay? So just to be clear about what this means, right? In the null, right, taking an arbitrary microhistory compatible with the coarse-graining, in general, people direct more aggression as you go further and further down. But in the actual data, over time, what happens is the emergence of this strategy, and the strategy is beat up on people just 1 or 2 ranks below you. People focus their aggression, or animals focus their aggression nearby them in rank. So another way to think of this, right, is the postdoc beats up on the graduate student, right? Okay, not on the undergraduate, right? The tenured faculty member picks on the junior faculty member, okay? But the tenured faculty member doesn't go, 20 ranks down and beat up on the high school student, okay? That's what would happen in the null. But the thing is we know how power works, and in fact, the intuition here, the fact that the birds do this is amazing. It's certainly our intuition. Okay, in the human case. Okay? And the claim here is that we're completing this causal pathway, right? The individual actions create power. Now remember, on the first quarter, it had no effect, right? It was consistent with null. But over time, that power feeds back to what the individuals know about the system, and their knowledge influences what they do. Okay? So I do not have time to tell you all the amazing things we do to show, in fact, that those cognitive and action pathways are in place, right? In order to complete the story, we have to show not only that there is this pattern, but a plausible way that that pattern could emerge. Okay? We think that they're studying network motifs. It's totally awesome, but I won't tell you. Okay? But the claim is, right, that downwards causation is possible. Features of the network that the birds can observe leads them to form beliefs, or enables them to form beliefs, and those beliefs predict the aggression patterns that they actually use. Okay? So let me just summarize here. Right, the journey I've taken you on, right? You know how to coarse-grain QED, okay? But you don't know how to coarse-grain a model of, let's say, a social system that has none of the symmetries and none of the strength, none of the theoretical strength of physics. So that's our problem, how to coarse-grain this process. I told you this story about the Krohn-Rhodes theorem, right, which enables you to coarse-grain a group, or in fact a semi-group, into equivalence classes. And in fact, what you get is you get this hierarchy. At the top of this hierarchy is a very coarse-grained representation of what's going on. The problem is that the top of the hierarchy is not necessarily the most important story that you're interested in. Okay? It might not tell you the facts you care about. And so what we have to do is we have to put in a story about what we care about and how much it hurts when you get it wrong. Okay? Once we do that, we go from the evolution of microstates to the evolution of macrostates, and one thing that happens is the theory becomes non-local. Long-range correlations emerge. Going more and more backwards into the past gives you better and better prediction. And that's an equivalent thing that happens when you coarse-grain, when you renormalize a Lagrangian, you get all these derivative terms coming out. I showed you a nice little story here about the case of the icing model, where we try to coarse-grain according to some observable we care about. And what happens is the coarse-graining fails actually at the critical point. At the extremes, when the system is highly ordered, coarse-graining is just fine. It's really easy. When the system is highly disordered, coarse-graining is just as bad as using the underlying model. There's no real difference. And in the middle, when the system is at critical, is where, in fact, knowledge of the microstates is most important or would be most useful to you. I finished with a bit of a rapid story that we get in the social world. And that rapid story is a story not just about how to go from here to here, which is all of this, but in fact how this top level actually feeds back. And I showed you some really exciting experimental evidence from Liz and I, and this is really Liz's data, okay, on how, in fact, the system learns to focus its aggression, how these high-level summaries of individual action feed back to influence behavior. So all that remains is just to put up a slide of my collaborators. Sarah is not a collaborator, but she is somebody who taught me a lot about information bottleneck and causal states, which is a story I told you. And to thank you for your time.
Let's take questions. Yeah, Rob.
So it occurred to me that perhaps another interesting example of top-down causation, which I'm reminded of because you're using the PageRank algorithm to calculate regression, would be in actual search engine results. You know, Google calculates PageRank and does other things to figure out how to rank web pages, and then the owners of those web pages do some search engine optimization to try to bump them above their competitors on that list. So they're using the top-level PageRank to decide, you know, how they're going to change their website, maybe change the links that they have on the website, which will influence the PageRank dynamics.
Absolutely. Yeah, I mean, this is a system we're very familiar with in the human case, right? When somebody tells you about the world, tells you a coarse-grained fact about the world, it's hard for it not to influence your behavior. If somebody tells you what the most important pages are on the web and actually shows them to other people, that's naturally going to influence how you behave if you care about winning that game. So it says, you know, the Google case would be lovely. I mean, Google, what it's constantly doing, right, is changing this map, right? They're in an like they no longer use PageRank, right? PageRank is only a minor part of their algorithm now, right? So they're in a sort of arms race against the people doing this, right? They're doing this and selling this pathway, right? And these other people are competing along this pathway here. Okay. So they're constantly trying to prevent themselves from essentially these kinds of situations here. So there you have even a competitive process. In the case here, the birds are actually using power. It's probably, at least Liz tells me because she's a biologist, it's probably adaptive for them to do this sort of thing, right? They're not going to evolve into an arms race where like one group is trying to hide facts about power and the other group is trying to find them out. So, but the story you tell about the, you know, in the human case, absolutely. I mean, we see it, you know, we see this in many different situations where we're told, for example, financial facts. We're told about a bank being shaky. Bank being shaky is a coarse-grained story about all the individuals involved in that bank and its full portfolio. But of course, we act on the basis of that coarse-grained knowledge. Yeah, absolutely. Yes?
Yes. Actually, you're talking about this network renormalization. So, but I think people in Khan's method has already kind of developed this kind of method for many years for network renormalization. For example, this tensor network renormalization. So for example, in that social network, you think about you have some local data on the vertices of the graph. So, but you can encode it by some tensor. And then you can read out this data by some observable. Basically, you can compute a correlation function and some kind of partition function, all kind of things. So actually, I'm wondering, in your network renormalization kind of scheme is talking about this cost function of the mutual information. And this mutual information in condensed matter, sometimes I think there's a relation between this density matrix. If you think about a classical system, you can always map to some lower dimensional quantum system, right? So for example, this 2D classical IC model, you can map to 1 plus 1D quantum transverse IC model. And then at the 0 temperature, we have precise definition for quantum entanglement. And basically the network renormalization based on the concept of entanglement renormalization. Get rid of the short-range entanglement and keep the long-range entanglement. And in this way, there are some very powerful methods. Even for critical IC model, you can still get a pretty good precision. So it's kind of some version of what the density matrix renormalization group has been developed by condensed matter people for 20 years, I think, from very early version.
I would disagree that what we're showing here is an example of network renormalization. What we're trying to predict here, the story we're trying to tell, is how to do coarse grading of a process and not just of the network itself. And so we're trying to figure out what the right dynamical theory is, how to simplify the dynamical theory to produce a forward time prediction. And if I understand your description correctly, it's distinct from what you're describing in the sense that we're not trying to simplify the network itself. We're trying to simplify the process on the network. But I also might misunderstand what you're saying. It might be a question that's better to take offline. Thank you. Yes?
Another question. So you, at one point, I think it was the second part of your talk, you described coarse-graining variables, but allowing non-Markovianity, so to get time. Probabilities can depend on multiple steps back in time to kind of reproduce better results, get a better approximation.
That's right.
And you're doing that in the context of a probabilistic model of something that maybe in the microdynamics was deterministic, and therefore there was an approximation. But I wonder whether there's another approach wherein you're doing an exact model and you're trading off coarse graining with how much memory you require. But you still retain an exact model, much like the Cohn-Rhodes decomposition is an exact model. And so I have an example in mind that maybe just try to make it more plausible. So if I do Hamiltonian dynamics and discretize time, I have a position and a momentum variable at every time. And if I coarse grain to just a position variable, but I allow the discrete time dynamics to depend on 2 steps back, well, Lagrangian mechanics allows me to do that. And it can model exactly the predictions of Hamiltonian mechanics. So that would be a candidate example of this category.
That's lovely, right? So it might be the case that I might have a Markovian or local theory, but some of the features of those states are harder to measure than others, right? So it might be easy to measure position, harder to measure momentum. And so, but I can trade off on that by having more deeper time data on one kind of feature of the phase space. Yeah, that's great. What you're talking about is, it's already interesting if you just talk about the lossless case, right? So I'm not actually losing any predicted power. I think that's what you're saying. I keep it exact. I don't know. This is a causal states story, right? And so I think one of the things we're saying is that the set of causal states might be degenerate, right? There might be two formulations of the system, right? Two different sets of causal states, both of which work equally well, right? One kind of causal state says, hey, if I know xt minus 1 and pt minus 1, states of that form, and another thing might be xt minus 1 and xt minus 2. And depending on your dynamics, these might be totally equivalent. I only need one set versus the other. I think when I think about what, for example, Jim and his collaborators do, my guess is that their systems are so jumbly, right, that they tend not to have degenerate cases like this. The fact that they show up in physics is, of course, intrinsically interesting. So there might be some interesting story to tell about the symmetries of causal states. There might be a large class of equivalent causal states that you can map to, and there might be some interesting stories about the symmetries that are there. That's a great, thank you very much. That's a great question.
Yeah, just one more question. This observation you made and you commented on, where by coarse-graining one produces normal catabolism time, is reminiscent of history, of course, where individuals do whatever they do, but they don't know much about the past, but societies do much about the past, and how to behave depends much on that past. So can you study this aspect of history using such formal concepts? Or is it just too much of a literary science?
That's a lovely idea. I mean, it's often easier to cash out. I'm gonna get my tea here. It's often easier to cash out these cognitive stories when you go to the animals, right? Like, this is such a clean thing, right? Take the birds, put them into a system, watch them discover facts about power, and use them, right? It's very hard to imagine a similar situation with humans because we have so much background, right? If you took 21 arbitrary, Canadians and they never put them in a room, it would be illegal, and it would also, your data would be swamped by their prejudices and priors and all sorts of facts, right? The birds have a little smaller memory. So when you talk about this trade-off between sort of lossy perception, right? There are things about you I don't know, but maybe I have memory, right? So if I watch you for long enough, I might be able to build up a better predictive model of what you're going to do. And if I'm not able to watch you, but I watch the coarse-grained variable, right? I watch facts about power, I might be able to gain if I remember back into the past. Because even if the individual actions are Markovian or approximate Markovian, when I coarse-grain that high up, memory matters. And so it might suggest that social animals, for example, have memories. Like there's a pressure to build memories of social facts. So that's how I would cash out in the biological case. I think in the human case, it's much harder, right? Because there's so many things going on that it's hard to isolate one set of facts from the other. We're just much more complicated. So.
But I thought it was your point to use such mathematical methods to study actual social systems.
Mm-hmm.
And you study Wikipedia.
Yes, yeah.
And you study human things as well. And so my question is, how ambitious can one be in being scientists or hard scientists when it comes to human social systems? Because you've tried.
No, this is a great question. Okay, so let me be a little more bold, right? So, okay, first thing is, right, animals are great, like, simple harmonic oscillators for humans, right? So you can do a lot there, and this is already really hard, right? But one question you might have is, when does a group become a society, right? And one joke is, right, you're in the elevator, it's just a group of people, right? But then if the elevator stops between floors and the lights go out, now it's a society, right? And so trying to understand that transition is really interesting. And I think one of the things you're saying is, okay, one way to study that transition is to look at the emergence of long-range memory, right? If these coarse-grained, I would claim, right, that the existence of these coarse-grained variables is a precondition for politics, is a precondition for societies to actually exist, right? And so if you don't have these, or if these don't matter, you just have a group, you just have a bunch of people. And so the idea would perhaps be, right, that if these start mattering, people are going to watch them over time. Okay? So people will begin to form, or be forced to form long-term memories of this, precisely because even if this is Markovian, this is not. And so if you look for long-range memory in the system, that might be a signature that a group, just a bunch of people on a bus, has become a society. So, okay, you're pushing me. I think it's a good question. I tend to be more conservative because I like to do statistical tests, and it's very hard to get random samples. But Wikipedia, for example, is the case where you can.
Any more questions? Well, let's thank you.
Thank you very much. Yeah.